Hi, this is Sarah.
And this is Omar. Welcome to the UCS B-Series solution training set. The UCS B-Series infrastructure is completely virtualized, and to accomplish such a goal, the hardware components must be fully abstracted. For example, a blade is just a piece of intelligent but deactivated hardware until it's associated with a virtual server. Similarly, the physical path between the blade and the FI must be abstracted, and a virtual circuit has to be created in order for the blade to communicate with the data center network resources. This virtual circuit consists of virtual interfaces on both ends and a virtual cable that connects these interfaces together. Bear in mind that the chassis and the IOMs are passive entities and have no independent management components, which means once the UCS system is cabled, all these mentioned tasks are handled by the UCS manager only, a true virtualized infrastructure. In this session, we are going to examine the virtual circuit components and the related best practices. So let's start on the FI side.
As we mentioned in part 1 of this series, the FI default port type is Ethernet, and the default status is unconfigured. So in order for it to become active, it has to be set to a specific mode, such as server or uplink. Obviously, the mode selection depends on the type of device connected to that port. The FI ports connected to the FEX modules are configured as server ports, and it can carry both Ethernet and FC traffic for many servers, VNICs, and VHBAs. So, on the FI, we need a mechanism to represent these server adapters, and that is done by using Software Virtual Interfaces, or VIFs. VIFs are spawned off the server's interfaces and instantiated on the FI. Without manual user configuration, the UCSM automatically allocates a VIF interface to the newly created VNIC or VHBA. The VIFs are allocated across all FI ports evenly in a static manner. To put it in a simple term, a VIF interface is a policy representation for the server adapter. So let's see how the FI uses it to handle external connectivity. Naturally, the FI's ports connected to the data center Ethernet component are set to uplink mode. As we mentioned, it's recommended to bundle these links in an Ether channel. End host mode is the default and recommended forwarding mode for the FIs, which comes with many operation benefits. Spanning tree is completely removed, which allows all uplinks to forward traffic for all VLANs, and the FI, being completely transparent, presents a set of hosts to the network that is accomplished by associating a server's VNIC with an uplink or Ether channel. Now, we recall that a VIF represents the VNIC on the FI. Therefore, the VIF is pinned to the uplink Ether channels in a persistent manner. Traffic between two servers' VNICs is switched locally on the FI using the corresponding VIFs. MAC learning and inter-uplinks forwarding are disabled on the uplink's Ether channel and moved down to the VIF's VNICs level. As we see here, the VIF is a fully functional endpoint of the server's virtual circuit. Each 8 adjacent ports on the FI are controlled by the same Unified Port Controller, or UPC. It's highly recommended to connect the FX links to the same UPC. VIF scalability for a blade is derived by the generation of the FI and FX, the number of the links, and the connectivity type. To maximize the number of available VIFs, the FI FX links must be connected to the same UPC and bundled in a port channel. Distributing the links across multiple UPCs significantly reduces the number of VIFs. Keep in mind that VIFs are used for VIC control traffic as well. Also, in case of a VNIC provision with failover configuration, 2 VIFs are needed. Now, let's examine the rest of the pieces.
The VIC 1280 comes with 8 10-gig Unified Fabric ports, or UFP. Similar to the FI and FEX UF ports, each VIC port carries Ethernet and FC traffic for many VNICs and VHBAs. There are two implicit flow-based port channels between the VIC and the FEX modules, providing 80 gig to the blade. Conveniently, no user manual configuration is needed. The UCS-M automatically sets the port channels when the VIC comes up. The VIC 1280 as a highly configurable and self-virtualized adapter can create up to 256 PCIe endpoints per adapter. These virtual PCIe endpoints are created in the adapter firmware and present fully compliant standard PCIe technology to the host OS or hypervisor. The PCIe cards can be configured as VNICs or VHPAs. It's important to know that, unlike VHPAs, a VNIC can be configured for fabric failover, though it will be active in one side only. The UFP implicit flow-based port channel allows a VNIC to burst up to 32 gig throughput, with a 10 gig limit per flow. VNICs and VHPAs are created when the blade is associated with a virtual server. The running hypervisor or OS has no knowledge of the underlying unified fabric infrastructure, and it treats the VNICs and VHPAs as regular server adapters. So, when we put all the pieces together and have a look at the full picture, we see that the virtual circuit is actually created automatically for us. A 6-byte tag or VN tag is used by the UF path to create the virtual cable between each PCIe and its corresponding VIF. VNICs and VHPAs come up when the virtual servers is associated to a blade and booted up. In another word, we only need to verify that the virtual circuit is up using UCS-M without worrying about any configuration. Cable once and follow the recommendation discussed here, and then move with confidence to creating virtual servers and bringing up blades. That sums up part 2 of the UCS B-Series solution. For more of this training set, you can check out part 3, Server Virtualization. Thanks everyone.